Hi guys, and welcome to Physics 4B. Today is Tuesday, April 6th. We're going to be doing more problems from this chapter. Let me check something quickly in here to make sure that I am on the right page in here. Hold on. Okay, anyway, so basically we have to continue the discussion that we started last time. I know we did, I think, like what, 5 problems so far. We did problems. On chapter 26. Let me move this thing out of the way. So I need to bookmark this page. Let me take this from here and let me go into chapter 26. Okay, so the problems we did so far are problems 19, I know for a fact, and problem also 29, problem 30, 31, and 32. So we have a total of 5 problems so far we covered. There are more problems that we need to cover off of this book, namely 4 more at least: problem 38, problem 47, problem 60, and problem 74. Okay, at least these problems that we need to cover for a total of about 9 problems that we think that we need to cover off of this chapter, which I hope that you guys will realize that this chapter is important since we're doing a lot of its applications. So when it comes to exam time, you guys really need to understand every single thing that we're doing in this chapter in terms of problems. So far, 5, we still at least have 4 more to go. Out of the 5 we did last time, there was 2 problems that bear some sort of a similarity, in a sense that you have a battery, and in that battery you don't know its magnitude, and you don't know its polarity also. So assume the polarity is correct, and we went through the calculation. And in the first case, it turns out the EMF turned out to be positive. So we said, okay, it must have been in the right direction because of the fact that the EMF was needed there in that direction to compute the current in the way that it was supposed to be going, and the voltage is everywhere. So in this case, keep the polarity the way it is. In other words, the anode of the battery and the cathode in the battery, or the negative, basically, the positive terminal and the negative terminal of the battery are in the right place. So do not tinker with them, do not mess with them, they're good. And the second calculation, in the second problem, and that would have been problem 32, what we actually, problem 32 or problem 31? Problem 32, I think, is the one when we did the calculation, it turns out that the polarity was wrong in the sense that the current, the voltage was there flipped. It was a negative number. So we really had to switch the polarity for that to work. So the value was correct, but it's the value, the sign that was wrong. So we needed to reverse the polarity. So that's in a sense what you do. Here is the deal. In general, when you're dealing with circuits, you assume some direction for the current, and you assume, if you don't know already, if it's not already stated, that the polarity is in this specific direction, or if they already stated that the current, we know specifically it's moving in this direction. According to the ammeter, the needle swings one way or the other depending on the direction of the current. So we know which direction its current is. So if it's known, you don't monkey with it. It's already given. But if it's not known, just make some directions and start working with it. And if the current turned out to be negative in this case, so your direction of the current was wrong, that's all. This is unlike what you guys did in physics 4A, when you were calculating accelerations and velocities and everything else, and where you're dealing with friction. If you have friction and you calculate the acceleration, and the value of the acceleration turned out to be negative, that at that point, you were supposed to abandon all calculations and redo the whole calculation again. Why? because you're assuming that the direction of the friction is opposite to the direction of motion. And now you have a direction of motion that is pointing in the wrong direction altogether. So in this case, it's not just a matter of doing what we're doing right now. It's not a matter of saying, oh, maybe the whole thing was just backward. No, actually, you had to abandon the calculation, start all over with a new set of assumptions on those problems, and work with the new set that maybe the particle was moving actually in the other direction, which means the friction is opposite to the direction of motion, and you calculate again the acceleration. Typically, in those situations with the first class of physics, physics 4A, you end up with the correct sign now. So in other words, you discover you were wrong in the beginning. But now the fact that you get the correct sign, and for the second part, you say, you know what? I am not wrong anymore. It doesn't mean that you're right. You could have made a mistake in the calculation, but you're not wrong in a sense, obviously wrong, like in the first case. Sometimes, though, with those tricky problems, and that's a nice discussion to have in physics 4A, you end up with a negative acceleration in the presence of friction. So you say, okay, you know what? I'm going to do the whole thing again, but changing directions. And now you end up with another negative direction, which is a nonsense in this case. So in this case, the object is probably not moving at all. Okay, so there is something else that must be at play. But I just wanted to make the connection here with this type of problems that we're dealing with in electricity. In a sense, we calculate the current, making an assumption on the current, if it's not already given. If it is given, then you don't have a choice. But if it is not given, then you make a direction and you start working with it. Same thing with the polarity of the battery. If it's not given, then you make an assumption and you start working with it. If the signs turn out to be positive, then everything is fine, provided you have checked your work and you didn't make any mistakes in the calculation. And sometimes it's the other way around. You actually find the signs opposite. So you see, you know what, the current is actually moving in the opposite direction and the battery needs to be flipped. So those are the two types of problems that we did so far. Namely, we did actually more than that. We did about 5 problems, and these 2 problems have that idea in it. So let's continue with these problems, and let me share with you the screen because I have far more problems that we need to talk about in this chapter. So, by the way, I don't think that, are you guys looking at what it says? Chapter 26 problems, and it's showing some sort of discussion that we had in the lab.
Yeah, it's showing last time's problems.
Okay, very good. So the problem that we have to do today is our problems 38. Hopefully we get through all of them. 47. Problem 60. And 74. Okay. 74 has an interest in terms of practical applications in the lab. Problem 58 I'm not going to do, but it's similar to problem 19, I believe. Problem 19 had the idea with the water, basically, and you want to heat it with a resistor. So you want to get the power. In problem 58, it's similar. As a matter of fact, it's almost identical, with the exception that you have the latent heat, in this case of water, for melting, because you have the water in ice form, and you would want to basically melt it. Okay, so you'd want to find the heat that needs to be added there, and the formula for it, for that problem, is the latent heat, basically, of fusion, is Q is equal to M times L. And L is given to you in here, which is equal to 3,000 or 3.34 times 10 to the power 5. That's how much energy is needed per kilogram to basically melt the ice. Okay, so obviously the problem there is that you need that much energy. So basically, problem 58. I'm just discussing problem 58. I'm not doing it so that you guys know. The circuit shown, resistor is embedded inside a large block of ice sitting at 0 degrees Celsius, and the battery has negligible internal resistance. At what rate in grams per cubic centimeter is the ice is melting? Once you find the energy, once you find the power is the rate at which this energy is being basically converted into to the ice. This is the rate at which the ice is melting in terms of the energy. All you have to do is divide by L, and you find how much actually grams per second is going to be melting if you have that is sitting in it. So that is the idea behind this problem, similar to problem 19. Okay, so let's continue. Problem 38. Where is 38? Here. So it says problem 38, you connect a battery. So by now, whether you're watching this one live, like you guys are in here, or you're going to watch it recorded, I assume that you're going to grab a piece of paper and a pencil and start working these things. As a matter of fact, you need a calculator too. And start working this problem. Do not rely on my calculations. And part of the stuff is you're going to check that you're actually doing this. Okay, no problem. Okay, it's too late, but he's coming back. Okay, good. Okay, no problem. So let me continue with this thing in here. So problem 38, it says you connect a battery, resistor, and a capacitor as shown in the figure 2620. So it's figure 2620, basically what you have an EMF. This is what we did in lecture actually, and a resistor R, and a capacitor Q, capacitor C. And usually you have a switch in the circuit, S, to start things on. This is usually triggered at equal to 0, okay? You turn on the switch, okay? And it says that the EMF is 36 volt. The resistor is 120 ohms. And the capacitance is 5 microfarads. And there are 3 sig figs in this problem, okay? 3 sig, sig figs play a major role when we're doing problems online, okay? Especially when we're doing exams online, and I think the second exam is going to be online. So please pay attention to the sig figs, okay? In this case, there are 3 sig figs everywhere in here. So the switch S, so that is the switch S, is closed at equal to 0. When the voltage across the capacitor is 8 volt. So initially there was no voltage across the capacitor because there was no charge, because the voltage across the capacitor is given by Q over C. This is the voltage across the capacitor between this point and this point. So it's a good idea to label things, okay? So I'm going to call, starting from here, I'm going to call the point A, going to point C, going to point B, B and then to C. And then this entire section is point C, by the way, when the switch is closed. So when the switch is closed, this entire section is C, this entire section is A, and this entire segment is B. So that's basically what these labels are. So this is indeed VB minus VC. This is this drop in potential, because I'm assuming there is a charge in here and negative Q in here. So I'm going from positive to negative in here, and that is basically what this drop in potential in here is. At some point during time t, at t, positive. This is how the circuit looks like. At t equal to 0, there was no charge in the capacitor. So we know the voltage drop was 0 immediately after we close the switch, because there was no charge in here. And in here, there is a current I across the resistor. As a matter of fact, the current I times R is the voltage drop across the this resistor. So V sub R, which is VA minus VB, is simply R times I. And the drop in potential between A and C is clearly equal to the EMF, because this is positive, this is negative. So VA minus VC is actually the EMF itself. Don't get confused with the fact if I am calculating VC minus VA, that is actually minus epsilon, because I will be rising in potential. So having it written this way, I can write now Kirchhoff's rule for this loop when it's closed. I'm going to go in the direction of the current. It's a good idea always to go in the same direction of the current. That way, you're keeping tab of the voltage drops. So I'm going to start with a point A. So I'm going to say VA minus VA. Obviously, this is 0. This is equal to VA minus VB plus VB minus VC plus VC minus VA. Okay. This is the drop across the resistor. So this is RI. Okay. This is the drop across the capacitor. That is VB minus VC. This is the negative of this value because I'm looking at VC minus VA, not VA minus VC. So this is actually a rise because I'm going from C to A. I'm rising by epsilon. This equation is keeping tab of the drop. So the rise in this case is a negative drop. That's all. Okay. So this whole thing must be equal to 0. And the question says in here, what is the question first? I forgot. I'm sorry. When the voltage across the capacitor is 8 volt, what is the magnitude of the current in the circuit? So this should give me an idea, an equation to finding the current, because I know that this is equal to 36 volts. So this is negative 36 volt. This one, they said now it's an 8 volt drop. And this added to RI must be equal to 0. So what I have in this case is RI. Obviously, 8 minus 36 is negative 28 volt, is equal to 0. This gives me I equals to 28 over R, and R is 120. So it's 28 volts over 120 ohms. This can be divided by 4, and this can be divided by 4. So actually, it can be divided by, so it's 7 over 30. So the current is 7 over 30 amps. I mean, approximately equal to, let me see, is my calculator open? Yes, it is. 7 over 30, which is 0.223 repeating, okay? So again, if I'm just worried about decimal points in here, and I'm using a calculator, I'm in like an online exam, this is probably what I do, 0.233, because that's the sig figs in here, okay? According to this calculator, the 3 is repeating in here. So anyway, this is actually a much easier way to writing it. It's I is equal to 7 over 30 amps, because I divided by 4, and I divided by 4, so it's 7 over 30. So far, does this make sense to you guys on how to find the current? It's just rewriting Ohm's law. I mean, Kirchhoff.
Yeah.
Okay.
Yeah, it makes sense.
Yeah, it makes a lot of sense.
Very good. As long as you're basically going from a point and coming back to it, keeping tab of the voltage drops from positive to negative, that is the EMF. From positive to negative, that is actually Q over C. They didn't ask us for Q, but we can find it. And they drop in here in the same direction of the current. Think of basically a waterfall. The waterfall is the water, and the height in this case is where it's falling from. So A is higher than B because the current is clearly indicated in this way. If it is positive, if I calculate it and I turn out to be negative, then that means the current is actually flowing in the opposite direction. But it's not good. It's in this correct direction. So this is actually a voltage drop, and I can calculate the voltage drop. The voltage drop is actually 28 volt, because there is a voltage drop between A and B this way of 36 volt, and there is a voltage drop in this way, which is just 8 volt. So this drop from here to here must be the difference, which is 28. So that's another way of looking at it. How much we're dropping from A to C. One way it's 28, and the other way also it must be 28. Since I mean, well, not 28, 36. This way is 36. This way also must be 36. Since this one is 8, the other one is just a difference between this and that. And that's exactly what this expression is saying. Okay. So we have found the current. That's part A. Part B, at what time T after the switch is closed is the voltage across the capacitor 8 volt? Initially, there was no voltage drop across the capacitor because of the fact that there was no charge. Q was 0 at T equal to 0. But then over time, charge is being built up on the capacitor. So there is a voltage that is increasing from 0 all the way to 8 volt at this point. So this is sometime in the future. We need to find this time T in the future. the rate with which we're putting charge is actually this current I. And if you look at the lecture, I is given by the EMF over R times exponential of minus T over RC. We defined RC as a time characteristic, which is just the product of the resistance times the capacitor. Resistance in this case is 120 ohms. The capacitors is 5 microfarads. So this is ohm. When you multiply the two, you're going to find 5 times 12 is 60 plus another 0. So it's 600 microseconds. Okay, it's a very, very short period of time. So if you're curious, trying to write this one in terms of algebraic, so is this 6 to 10 to the power 2 times 10 to the negative 4. So this is actually 6 times 10 to the power negative 6, I'm sorry, plus 2, that's negative 4. So it's 10 to the negative 4 times 6 seconds, 0.6 milliseconds. That's the time with which the characteristic. This is the time characteristic. In other words, the current starts like this. Starts as epsilon over R. And epsilon over R, the biggest current in the circuit, is going to be 36 divided by 120. This is divisible by 6, leaves me 20. This is divisible by 6, leaves me 6. 6 divided by 2, that's 3. 3 divided by 10, that is 0.3. So it starts with 0.3 amps. That is the biggest current. And it starts to drop with time exponentially. At some point now, the voltage is 8 volts and the current has dropped to 0.23 amps. I wrote it's very, very high in the process. If this is 0.3, so this is 0.1 probably, and this is 0.2, this is 0.23. This is the time. Sorry. So this is the T that we want to find. So this is the T naught that we need to find because the current dropped to 0.23 amps. It did not drop a lot, okay? So it's still kind of high, relatively speaking, because if this is 0.1, this is 0.2, and that is 0.3 on this scale. So this is the current where it sits right now, 0.23 amps. That is when the voltage was 8 volts in the capacitor. So we need to find that time. Obviously, the time T, when we drop by an E, when T is equal to tau, we drop by 1 over E, 1/3 of this value. We drop almost to this point. So this is tau, actually, which is 600 milliseconds, microseconds. If I went another tau, I'm going to drop by 1 over E squared, or 1/10 of this value, roughly about 1/10 of this value. So if I went another tau, so this is 2 tau. So we're going to be here. If I wait 3 tau, it's going to be 1 over 30th. So we're looking at somewhere in here. And so on and so forth. So because this is an exponential decay, I mean, it's clearly that this time should be, at least through the graph, less than tau. We did not wait 600 microseconds to reach that voltage. Okay? Because the voltage did not go, because the maximum voltage is 36 volts. That's the battery. And it's putting charge on the capacitor. As it's putting charge on the capacitor, the voltage on the capacitor starts to grow. When it reaches saturation, the voltage across it will be exactly equal to 36 volts, and it will kill the current. And that is what's going to happen at the end. So there will be no more current when we wait too long. Okay? So this is basically how we're charging this capacitor. So we need to find this time. So here is the equation that we need to solve. At when VC is equal to 8 volts, we found I to be equal to 7 over 30 amps. This must be equal to, this is the time, T equal to T naught. So this must be equal to epsilon over R times exponential of minus T over tau, which is RC, okay? And epsilon over R is that number that I just wrote, which is 3 over 10. So this 7 over 30 must be equal to, what is it, 3 over 10 times exponential of negative T over 600 microseconds, okay? So this is an equation. Now, obviously, this time has to be T naught now, and this is met, okay? Okay, the 10 and the 30 cancel the zeros. And basically, I will have 7/9. 7/9 equals to exponential of negative T naught over 600 microseconds. I could leave it in terms of tau, actually, but that's fine. So I'm going to take the natural log of both sides. Ln of 7/9 is equal to the ln of the exponential is just the exponent. And from here, it gives me an equation for T naught equals to negative 600 microseconds times the natural log of 7/9. 7/9 is less than 1, which means that its natural log is negative times the negative is going to be exactly positive. And we need something to happen in the future, because after all, at T equal to 0, we close the switch. So this has to be positive time. It cannot be a negative time. So this is why during the exam, you need to bring a calculator with you. You need to bring a pencil and a calculator. Bring a spare of pencil, 2 pencils, okay, just to make sure that everything is sharp and everything is ready and everything else. Honestly, I don't know about the room where we're going to have the exam, whether or not we'll have sharpeners in there or something, but bring at least that. I will provide the scratch paper. I will provide actually the problems, and I will also provide the places where to write the answers to the questions, and I will also provide the formulas for you guys. So you will have formulas in physics that you will need to do the, I don't want you to memorize formulas. That is not the purpose of this class at all. So you're going to have the formulas you will need, whether those formulas in physics, whether in math, for example, famous integrals, and how their integrals are, and also trig identities and relationships that you will need for your exam. Is this clear?
Yes, it is.
So
Yes.
bring a calculator though, calculator that can do this kind of calculations. So it's very important that you have to have something that has the natural log in it and things like that. So if I plug these numbers in here, I'm going to find T naught. Okay, I'm going to plug it with the negative sign and everything. So it's going to be negative 600. I'm going to leave the microseconds, okay, because I know this is going to happen so fast. The natural log of 7/9. Okay. And the answer is 150.7888. Since I'm dealing with the 3 sig fix, I'm going to call this one 151 microseconds. So it's a positive time, and it has to be. It cannot be a negative time. And it's less than 600 as I thought, okay? It's less than 600 by a factor of almost what, 4? So this time in here is about 1/4 of the overall tau. Obviously, if I wait tau, this current will drop drastically to almost 1/10 of an amp. Right now, it's when we started, it was 3/10 of an amp. Okay, so it's factored by the factor of E, and E is 2.71 whatever. So it's roughly about 1/3. Okay, it drops by that factor. So this is a time scale when this happens. Okay. So we answer the second part, part C now. So this is part B, by the way. If you are curious trying to write it in terms of seconds, obviously this is 1.51 times 10 to the negative 4. No. Yeah.
Isn't it to the 6? Because microseconds, or are you taking into account that it's into the hundreds place?
I put the decimal point.
Oh, okay.
That's the scientific notation, okay? 1.51. Okay?
Right. Yeah.
So that's just another way of writing it. Okay, so this is the, it's a very, very short time, basically. That's the point. In no time at all, the voltage went from 0 all the way to 8 volts in the capacitor. So that's basically what the moral of the story is. So when the voltage across the capacitor is 8 volts, we're still at this time scale. At what rate is the energy being stored in the capacitor? Okay, part C. The energy in the capacitor, if you guys remember, is Q² over 2C. This is the energy. the rate at which the energy is being dumped into the capacitor is just the derivative of this term with respect to time. And so we need to take remember Q is a function of time. So we need to take this derivative with respect to time. So the P, and capacitor, that's what the C stands for in here. This is the power. That is what the rate of the energy is. It's the power. It's going to be 2 coming from this derivative times Q divided by 2C times the derivative of Q with respect to T. 2 cancels the 2. And dQ over dt is actually I. This is the current I. So this is Q over C times I. And Q over C is actually VC, which is 8 volt. So this number is 8 volt. And this number, we just computed it to be 0.233 repeating. So we know the current and we know the voltage. So all I have to do is just multiply 8 times 7 divided by 30. So this is 8 times 7 divided by 30, because that's exactly what 0.233 is. So it's going to be some fraction. So 8 times 7 divided by 30 is 1.87. Again, I'm using 3 sig figs, watts. Okay. Which brings me to an essential point in here. And again, I'm just emphasizing on the stuff that you need to do. So the point that I want you guys to remember as the discussion thing is, please bring a calculator that is basically a scientific calculator, and at least a pencil, hopefully 2, sharpened and ready to go in the exam. Do not bring any scratch paper or any formula sheets or anything like that, okay? But there is another thing in here at play. If I multiply this 2, I get 1.87. If I multiply the other 2 number, the one that has already the rounding done to it, 0.233, the answer is going to be 1.86. Okay, obviously this one actually was not 1.87, which was 1.866 repeating. This one is actually 1.864. So it rounds actually to 1.86. It's a good idea not to round stuff until the end, like this one, but if in case you do it this way. Here is the deal, though. It's very important when you're doing exams, okay, and homework problems and everything else that you're going to submit to me. You need to show your work. Because if you rounded somewhere and you rounded wrong, or you miscalculated somewhere, and instead of, for example, calculating this current correctly, you forgot that there is a microsecond in here and you ended up with 151 seconds or 151 years or something like that, which is nonsense. But then if I don't see your work, and in fact that you forgot a micro somewhere, or you forgot to multiply in here by microfarad and you thought it's a 5 farads already, then I have no way. I have no way of finding where you went wrong. And then imagine that this equation now has an impact on something else, okay? So not only you lost points in this question, but you lost points in the question after that because it's completely wrong. You don't show me what you're doing and how you're doing it. So I only am going to assume that you have no clue what you're doing. That's the only natural, basically, assumption. Even if you look at your own work, you probably wouldn't remember exactly how you got those numbers, okay? And you would assume that you did it wrong too. And then it could have consequences in several other questions down the road. And then at the end, you basically wasted a lot of good work for nothing. But if you show your work, let's say, for example, I find what the error is. Here is where the problem is. The steps following are all correct. You might get the full credit, or at least a great deal of the credit, for the next steps, if you show, of course, that you're doing them correct. And the step after that, and the step after that. You lose only points during this nonsense probably place, but then you will get a lot of credit for the problem. So showing your work is critical, and submitting your full detailed work is very, very important when you're doing problems like this one, because I don't grade on the results. I don't grade on the answer, the final answer. That is not true. Okay? As a matter of fact, sometimes you lose points just because you got the correct answer and you didn't show the steps because you're required to. Okay? In other words, I want to see the argument for it, not just because you guessed. Like, for example, the question that we had before, where you're supposed to find the direction of the voltage, you could at least take a 50% chance and say it's going this way or the other. And you could end up with the correct answer. But the whole point of that question is not about the answer. It's about the justification for it. So the fact that you guessed and you guessed right has no bearing whatsoever in this case in here on the actual problem. So I really want to see you guys. Obviously, you'll get some credit, especially if it's a number like this one, and you somehow guessed and guessed it right. Then maybe you can get credit for, provided you did not have any help. Okay. By the way, and I mentioned that you will have different versions of the exam anyway, so I'm not worried about that. Okay. Is my point clear in terms of showing work and things like that?
Yeah, it's clear there.
I know it's a lot of people, they make emphasis, they make a big fuss over two, and that's important. Actually, it's not just. So this is the rate of how much there was other questions that were not asked, but we could have asked them. For example, how much charge is inside the capacitor at this point? Well, the charge is given by, remember, V in the capacitor, which is 8 volt, is equal to Q over C, I'm sorry, which gives me that Q is equal to CV, and Q then is equal to C, which is 5 microfarads, times the volt, which is 8 volt. And then 8 times 5 is 40. So this is 40 microcoulombs. So we could have asked that question. We could have even asked how much energy is stored, just to not to confuse it with the power with which we're putting energy in. This is the rate at which energy is being built, because after all, the capacitor is a device to store energy. So that's really the whole purpose of it. So we want to make sure how much energy is stored. So the energy that is actually stored in the capacitor at this point, it's Q squared over 2C. Another way of writing this expression again is that Q over C is just V. So it's going to be VQ, I'm sorry, over C, over 2. And V is 8 volt over 2 times this 40 micro coulomb. 40, not 4. Okay? Because Q over C is V, and that's 8 volt. Okay? So you'll be left with another Q divided by 2. So you have 4 times 8, that's 32, 320 divided by 2, that is 160 microjoules. So that's how much energy is stored so far in the capacitor, okay? So that is another question, which is already gained. And we're putting energy at this instant because it changes with I. This expression changes with I and also Q. So this depends on Q times I, because Q is piling up and I is going down. So the rate is going to change with time. The rate is going to change with time. We're going to start putting up a lot of charge initially, and then as the current drains, we're not going to be putting much energy. So at this point, this is the rate with which putting energy. So if we wait very, very long time, ultimately this expression will go to 0. So we will not be putting any more energy at the end in the capacitor, because it's going to saturate at some value, not necessarily this one. This is just at that instant after 151 microseconds. I think this problem we did it to death. We overkilled it, but I'm hoping that you guys have a better understanding now and appreciation of this process with numbers in. Okay, so the next problem I promised is problem 47. Let's do that. In problem 47, it looks daunting. It looks complicated. Okay, and sometimes looks are deceiving. So that's really true in this case. So what I have in here, I have a battery, and the battery is a 100-volt battery. Here it seems like I have 4 sig figs. Actually 3, because the next 2 are actually showing only 3, or 1 decimal point. Okay, so I have a capacitor in here, but it's in parallel with a resistor. And this resistor is 25 ohms. And this capacitor is 15 microfarads. Okay. After the junction, we have another resistor, and that resistor is 75 ohms. And now we have a junction. In one branch, I have a capacitor of 20 microfarads, followed by a resistor of 50 ohms. Okay, this is the other branch. In the other branch, again, I have another junction. In that junction, I have a 25 ohm resistor. So this is 25 ohm. And I have a capacitor now. And this capacitor is 10 microfarads. And then the junction again. And finally, I have actually in here another resistor of 25 ohms. And this is another junction actually. And to close this whole thing, I have a switch. I mean, I have a another 15 ohm resistor. But before that, actually, I have an ammeter to register current. And we have a switch, which we're going to put in here. So this is the switch S. Okay. Obviously, if the switch is open, there is no current flowing because it's coming from the battery, and the battery is disconnected at this point. So there is nothing flowing through the whole circuit. Okay. Did I miss any of the labels? No. So this problem has 2 questions and 2 questions only. To find the current in through the ammeter, that's all. That is our problem. Find I. So there is a current that is going to be flowing through this one in here, and that is to find it. A, immediately after T equals closed. So after T equal to 0, immediately, very close from T equal to 0, actually, when we close the circuit. And then when we wait for forever, okay, then B, when T is very large, okay? Compared to what? Compared to tau, actually. There is a characteristic tau in here, albeit we have several capacitors and several resistors, but you can reduce the whole circuit actually to an RC circuit. We're not going to do that, but we're going to find these 2 currents. The first one, immediately after after the circuit is closed, there is no charge in this capacitor. So this acts as a wire, which will short circuit this resistor. So this resistor as if it doesn't exist, because the current comes in here and all of it will go through this capacitor because this is short circuited. So there is no current in here that is going to go through this one. It's equal to 0 as a matter of fact. So all of the current will fly through this one, then goes through this 75 ohms. So the 25 does not exist at this point immediately after T equal to 0. Then also these points are actually short-circuited too, because there is no voltage in here. There is no charge. And the voltage is actually Q over C. Since this is equal to 0, this is equal to 0 immediately, okay? So there was no initial charge in the capacitors. So this is actually short-circuited. The current that is coming in here after the 75 ohms will split itself, partly will go in here, and the other part will come in here. When it finds this junction, the circuit actually, the current will go through here again. Nothing will go through this portion of the circuit because, again, it's short-circuited in here. So the easy path is through this point. So this resistor, as if it's not there at all. So you're going to skip through it this way, through the current, and come in here. So what you have in the circuit, as if you have this 50 ohms sitting in this junction. In this very same junction, the current goes through this way, comes in here, and you have another 25 ohms. As if the 50 and the 25, they're actually in parallel. Their equivalent resistance is 1 over 50 plus 1 over 25 inverted. If we do the calculation, 1 over 25, the common denominator is 50. So it's going to be 2 plus 1, that's 3. 3 over 50. When you invert it, it's going to be 50 over 3 ohms. So this is the equivalent capacitor, the equivalent resistor in this case, because they are in parallel. And that is the sum of these 2 resistors, basically effective resistance, so which is 50 over 3 is what? 10 over 3 is 0.3 times 5. So it's a small resistors. How much is 50 over 3? 51 over 17, so it's slightly less than 17. 16.67. 16 and 2/3 of an ohm. So this as if it's 16 point, basically 50 over 3 ohms. Now here was the story of the current then. It goes through this and comes through the effective resistor. Here is the effective resistor. This is 50 over 3. Of course, we replaced this by that and replaced that by this. So both of them are not there. So the only thing that is there is the effective resistance, which is their equivalent. So we have a current that comes through this one. There is no resistance in here. The first resistance is going to encounter is 75 ohms. So the EMF, I can take any point in here and it's going to be the same thing. It's going to be 100 equals to 75 plus, because it's in series now with this 50 over 3, 50 over 3, plus it's in series with the 15 now ohms. And this whole thing times I will give me the current being equal to I is equal to basically 100 over that whole bunch of stuff, which is 75 plus 50 over 3 plus 15. And so if I do the calculator, I'm going to leave it as 50 over 3. I'm not going to replace it by its value. 100 divided by open parentheses 75 plus 50 over 3 plus 15 and close the parentheses. Okay, it's telling me that the current right now is 0.938. I'm rounding it and just keeping the 3 sig figs, okay, amps. Okay. That's how much current is flowing through the circuit immediately. Now, if I wait for a long time, for the second part, this will be fully charged. When it's fully charged, it's not going to accept any more charges. So it's going to kill the current going through it. So this will act as an open circuit. So the current tries to come in here and nothing will go through this way. All the current actually will travel this way. Go through the 25 ohms and come through this way. And when it tries to go here, this is fully charged. When it's fully charged, again, it's going to kill the current running through it. So in here, it's going to act as just an open circuit, as if you have a switch in here and you opened it. So there is no current flying through this one. This is I equal to 0. Because of this situation here, this is fully charged. So we're going to kill the current going through it. Again, when the current comes in here, which is the same current that went through 25 ohm now, so this doesn't exist. This whole section doesn't exist now anymore. And then the current comes in here and tries to go through this junction. It finds that this is fully charged also. Since it's fully charged, as if it's not there. Again, it's not going to accept any more current going through it. So I is equal to 0. All the same current that went through this 25 ohm and the 75 ohm must go through this 25 ohm. Oh, I'm sorry. Did I forget the other 25? Oh man, did I forget that? Oh, this calculation is wrong. I'm sorry, guys. This calculation is wrong. Hopefully you guys need to pay attention to what I was doing. So I have the 75 going through short circuited. There is a 25. Oh yeah, we did the equivalent. I'm sorry. We did the equivalent. That was the 50 over 3. So this is good. The calculation is correct. For a second, I thought that we forgot to include this 25. So we did it when we did the equivalent resistor between the 50 and 25, and that is there. So we included it in the calculation. So sorry about that. But let's continue now. So basically, the current comes in here, and there's a junction, but nothing will fly through this one because this is fully charged. It's not going to take any more charges, so it's going to kill the current. So this will act as an open circuit again. It's as if it's not there. There is nothing in there. So the current will go through this resistor of 25 ohms, comes through for it and go through the other 25 and comes in here. There is no current coming from this section at all because it's open. So all of the current will go through the 25 ohms. So now the calculation is slightly different. So it's still the 100. And I have the 25 is in series with the 50, is in series with this 25, is in series with this 25, is in series with this 15. So the current now is going to be, again, 25, the top 25, this one. The current must go through it because this is now closed, open, okay? Plus the 75. Nothing is going to go through here, this section, because there is a capacitor that's going to kill the current. Plus the 25 plus 25 plus 15. Plus 25 plus 25 plus 15 the whole thing times I, and this is how we can find the current now. So the current now is equal to 100 divided by 25 plus 75 plus 25 plus 25 plus 15. And this is the current. So I'm going to do this one a little bit in here. So what we're saying in here is 100 divided by open parentheses. I have 25 plus 75. When in doubt, always write things explicitly. Do not try to do mental math because that's how I myself make mistakes. Okay, I know 25 plus 75 is 100, but I don't want to do that because I might make a mistake. And that's how I recommend things like this ones to be done. So it's setting 0.6060606. So the value is 0.606 amps, basically. Repeating 0606 after that. So here is the moral of the story in here. That is, first of all, how to handle capacitors and resistors immediately after and you wait for a long time when they're fully charged and they kill the current. This is how you treat them. Immediately thereafter, they're short circuit. So they short circuit the branch where they are at. So there was a resistor in here, but it's short circuited. It's like you run a wire through it so that basically no current will go through the other one. Okay, so it's short circuited in this case. Same thing in here. This junction in here is short. This section in here of this branch is short circuited, and this one actually is short circuited in here, as if this resistor doesn't exist. Now, when you wait a long time, they act like a switch actually that opens. So in this case, they don't let any current through them because they are fully charged. So it opens the circuit in here, so the current is forced to go through the 25 ohms. It comes in here, it cannot go through it because it's, again, open. Cannot go through this section because it's open now, so it has to go through the other 25 ohms and complete its path. So that is how we treat problems with capacitors when immediately after short diameter. So that's the reading of the ammeter. This is different, though, than the problem that we had before, the problem before that. When we were actually building a charge in the capacitor, we saw that the current starts with the finite value. If you guys remember, it was 0.3 amps and drops to 0 after it's fully charged. In here, it starts with a finite value, 9, or is it 0.9? I think I made a mistake in here. It cannot be 9 amps, is it? 0.9, I'm sorry. You guys need to check my calculation. This is not correct. 0.9 amps. It cannot be that high of a current. So this is the correct answer is 0.938 amps. That's too much of a current, 9 amps. I just looked at the calculation. It's showing me 0.9, not. Okay. So it starts with almost an amp and then dropped by a little over half an amp. And that is the other moral of the story. You have to keep track of these things, that it does not necessarily go to 0, even though you're charging capacitors, and you did at the end of the day, and you can find exactly how much charge in here is. If you're asked how much charge in here is, well, you know what the current is, 0.606, that is running through the 25 ohms, and that is the voltage across this N2. And that voltage, you can find it to being Q over C, and you know what C is, so you can find what that Q is, okay? Same thing. You can find what this voltage between this point and this point is just by looking at this whole voltage, which is 25 plus 25 times the current, which is 0.606, so that's going to be 50 times 0.606, and that is the voltage across these 2 points. And there is equal to this charge over that capacitor. So you can find that charge because you multiply this by the voltage drop. If you're trying to find how much charge is this in 10 microfarad, then you know also the current times 25, which is 0.606 times 25, is the same voltage drop across this end. And from here, you can find what that charge is. So you can find the charges, you can find the energies, you can find everything you like to find on this system at this point. And you did it. You did it with 100 volts. You charged 3 capacitors at the same time. Each and every one of them has its own charge. But the point being in here is that the current does not drop to 0 at the end of the day because there is still a path for it to go. So it goes through the 25, the 75, the 25, the 25, and closes back through the 15 and comes back through the battery. So there will be current still running through the circuit after all 3 capacitors are charged. Okay, hopefully this problem makes sense to you guys. Good?
Yep, all good here.
Yes.
Very good. Very good. So I'm going to skip to problem 74 because of its importance in praxis. And then we're going to come back to problem 16. Problem 74. Let me change back to regular color. So in this problem, what we have in here, we have a battery that we really don't care for at the end of the day, but we need it. So it doesn't matter what the EMF is. We have a point in here where the circuit breaks. And we're going to put a resistor that we can play with its resistance. We're going to call this a resistor N. So the value of this resistance is N. We're going to come back into this resistor and we're going to call it P. Okay, and then we connect this two to a galvanometer. So what is a galvanometer? Galvanometer is a special ammeter. It measures very, very weak currents. Okay, and we need weak currents in here because, as a matter of fact, we need them to be zero. So if we bring a regular ammeter in here, it's going to give me a reading of zero, but maybe there is a current in there. Okay, so that does not really yield for high precision measurements. So we still have a switch in here. And we bring a resistor that we don't know its value, but we want to calculate it. So this is the X resistor. And then we have another resistor that we know its value, or at least we can play with it. Okay. This is the M resistor. And we connect back the switch to, we connect back the circuit. And in here, we're going to have the switch S. So this is a lab that you guys do, at least in some other places we used to do this lab. To find the value of X, if you know what the values of N and P. Usually you just tinker with one of them. You play with one of the resistors, okay? You change its value until you find that there is no current going through the galvanometer. At that point, you can calculate what the value of X is. You can find what the value of this resistor is. So this is called the Wheatstone bridge. And it's, let's call this numbers A. Where is the B in here? This is B. C, D. So what we want to achieve is the following, that there is no current going from B to C or from C to D. From B to C or C to B, doesn't matter, going one way or the other. At the end, there is no current. Or if there is one going one way, there is another one exactly equal to it in opposite direction so that they cancel each other. So that's the moral of the story. There will be nothing going through that portion in there, okay? There is a problem here that I thought we were supposed to do. For some reason, I don't see it. Oh, I'll try to remember. I may have skipped a problem that I, because it hit me right just because when I was thinking about this question. Anyway, so we'll find it. So here is a question. Can we do that? Okay, that is the question. So here is the deal. We're going to take a point in here from A back to A. So we're going to calculate in here VA minus VA. I know that is equal to 0. Okay. So I can go from here through the N to this section in here. The current in here is 0. Current in here also is 0. So it doesn't matter which way you write it, 0 is 0. It doesn't matter which way you point it. So the current that goes through the N, I'm going to call I1. I1 comes in here. In this junction, nothing will go through this way or come from the other side. So the entire I1 by conservation of charge must be here. So this is the same current that goes through the N will go through the M and come back in here through the resistor. Okay. Now I2, I'm going to call this one I2. And again, I2, nothing will go through from the other side. Because of the conservation of charge, there must be another I2 in here. Obviously, this current in here is going to be the sum of I1 plus I2. And when they come in here, they're going to split again, and they meet again in point D. So they split in A and they come back in D. Okay. So I'm keeping tab of the voltage drop. So I'm going to look into this loop, the first one, and again I am going to follow the the current. So I'm going to go clockwise. So if I'm going to start from A, I'm going to go through the inner one. So I will have N times I, Ni, plus M times I1. And in this case, we're going to rise in potential. So it's going to be minus epsilon is equal to 0. So this is equation 1. I'm going to come to this equation now for the outer one and do the same thing. So I'm going to say that in this case that P times I2, Pi2, plus X times I2 minus epsilon again, because I'm going to rise in potential, is equal to 0. Or I could have done this inner loop and end of the story. We could have done the inner loop and that's it. So for the inner loop, this is how it looks like. So I'm going to write it in blue because we're going to end up with the same equation. So we're going to take a direction in this case, it doesn't matter. So I'm going to take it in this way, counterclockwise. Start from A still, because we're saying A from A to A. So we're going to from A to B, it's going to be Ni1. I'm going to come down in here on this side in the same direction of I1 because we're going counterclockwise. So it's going to be plus Mi1. Now watch what's going to happen in here. We're going to go against the current. I1 is raining down and we're going uphill against the current. So it's going to be minus X times I2, minus Xi2 to C. And from C to A, we're going to go against the current again, I2. And that is P times I2, minus P times I2. Minus P times I2, I'm sorry. That is equal to 0. There is no EMF in this branch at all, in this side in here, in this loop at all. So I have 3 equations with a bunch of unknowns, but the point being in here is that this is a redundancy of this 2. Because if I take the epsilon to both sides, these are the same equation. If I write it as N plus M times I1 is equal to P plus X times I2. So there is always one too many equations when you do problems like this one. So this is one equation. This is actually going to be equation 1. I'm going to work out another equation in here. Since I know that B and C are in the same potential, the reason why they are the same potential because there is no current between them. I can calculate VB minus VC, and I know it's equal to the current that is flowing through them times the resistance. And here it doesn't matter what the resistance of these wires and the galvanometer and all of that being very small. So it's going to be a 0 voltage. So the point B and C are in the same potential because there is no current. They're connected, and there is no current between them. So they must be in the same potential. Because of that, I can say that VB is equal to VC. Because their difference is equal to 0. So if I subtract VA from both of them, VB minus VA, that is still an identity. Well, VB minus VC, it's this drop in potential. It's N times I1. Or actually it's minus, it doesn't matter. It's minus, because actually it's B is lower in potential than A. So this is actually a negative negative N times I1, negative N times I1 equals to, again, same thing. The current is raining this way. Since it's raining this way, I'm going to, C is lower potential than A. So this is the drop in potential is going to be minus P times I2. So this is minus PI2. Again, why do I keep on writing X? Yeah, I2. Okay, this is equation number 2. What I'm going to do is take equation number 1 and divide it by equation number 2. Obviously, the negative sign will cancel because it's on both sides of the equation 2. So 1 divided by equation 2. Okay, this is the cancellation. I1 and I1 cancel. And I2 and I2 cancel. This negative and this negative will cancel because they are on the same side of the equation. So what I will be left with is N plus M over N is equal to P plus X over P. And that means that I have N over N, which is 1, plus M over N is equal to P over 2P, which is 1, plus X over P. Cancel the 1 from both sides. And I will end up with the equation that is actually asked for me, namely M over N is equal to X over P, or the unknown resistor is going to be PM over N. And this is what we want to demonstrate. This is what we needed to show. Okay. Sometimes you'll find this expression written extensively in physics. CQFD, which stands for the French way of saying what needs to be shown. Okay. Ce qu'il fallait not for. Basically what needs to be shown, okay? Forget about this. This is what we were asked to show, okay? So this is what we were supposed to show. That's the question actually that we were supposed to show. Show that X is equal to MP divided by N, and that is exactly the same expression, PM divided by N. Here is another thing that you're going to also remember when you're doing exams, okay? It's very important. If the galvanometer shows zero deflection, when M is equal to 850, so they gave you M is 850 ohms, and N is equal to 15 ohms, okay. 0.0 in here, okay? Let's make sure that I have 4 sig figs and 4 sig figs in here. And P has also 4 sig figs, 33.48 ohms. Looks like from these numbers that we were playing with P all along. We were changing P. What is the value of the unknown resistance X? Let me tell you my point in here. It's a very important point that you guys need to remember for your exams, okay? And this is true for physics or any other subject. So obviously this is just multiplying 850 times 33.48 divided by 15, and I really don't care about the answer at this point at all. What I care about is the following very, very important point. If you're asked to prove a formula or show something, like in this case, show that X is equal to, and you're struggling with it, and you try to think about it, and you saw that time is slipping, time is not really to your advantage. But immediately there is another question after that one, which really says, like, for example, if M is this and N is that and P is that, what is X? Why didn't you tackle that? It's worth some points. Do that, assume that it's correct, and plug in the numbers and get yourself at least some points out of the way. And then go when you have time and try to think of a way to prove it. Obviously, hopefully, the further you are in the proof, the better you're going to be. That is a very important point that you guys need to remember when you're doing problem solving in general, not just for physics. If you're asked to prove something, especially in an exam when there is a lot of anxiety and then a lot of focus and probably did I forget to do this and that, and take advantage of this. Do it right away. Yes?
Yeah. So tackle what is easier to you and then go back and revisit it when you have it all down.
If I have a question as A and B, I would answer B first. B, X equals 2. Plug in the numbers. Okay. 850 times 33.48 divided by 15. And that should be 1,897 because it's giving me more sig figs than what I need. Okay. And don't forget the units. You lose points with me when you forget units. Okay. So it's 1,897 ohms. Because you're, for some reason, you're keeping tab of 4 sig figs. 0.2 according to the calculator. Okay. So I hope that that also brings up some valuable points in here and pointers when you're doing problems like this one. Just take the easy one first because it's already there. I mean, it's like dessert waiting to be taken. It's probably not the main course, but take that and then go back into the main dish in here for this problem. Probably there is an emphasis in here on understanding what's going on. And the key point for this problem, and there is always a key point somewhere, is this relationship actually between B and C. The key point in here, since there is no current flowing through this section, that these 2 points have the same voltage. Everything else is standard. Everything else is just algebra, okay? The key point for this one is the fact that there is no current flowing through the galvanometer. That means the points C and B, since they're connected, must be in the same voltage. So that is the key in this case. That is what breaks what breaks open this problem completely. That is what with which you can solve this problem. Okay. Everything else should be straightforward after that. Okay. Problem 60 now. We're doing in time. We still have plenty of time to do this problem, hopefully. Okay. Problem 60. What we have in here, let me draw the show the shape in here. So we have another type of problems that deals with batteries again. I have 24-volt battery, and I have another battery in here that does not show its EMF. It's telling it's an EMF epsilon. And there is a 7 ohm resistor in here. Okay. There is a 2 ohm resistor in here. Connect these two. And connect, there is actually another resistor in here of 3 ohms. My convention, it doesn't have to be yours in here, is that this current that is going through it, I'm going to call it 3 ohms, okay? Once I know its direction. The one that is going through the 7 ohms, I probably would call it I7. And the one that is going through the 2, I'm going to call it I2. You don't have to go with this one. You can call them I1, I2, I3 until you exhaust all of the indices, okay? As much as you want. You don't have to go with this convention. So you don't have to stick with the way I'm doing it, because sometimes it might be confusing, hopefully you're not. But if you are, please let me know, okay? So it says that what must the EMF epsilon in the figure be in order for the current through the 7 ohms resistor to be 1.8 amps? So there is a current of 1.8 amp in here. Okay, and we want to know what the EMF is. Each EMF source has negligible internal resistance. So basically, that's the only question. That's a simple question. And if you look at the problem, I mean, usually the book gives them points in here for difficulty and everything else. This one has the highest points in terms of difficulty. It's far more difficult than the Wheatstone bridge, for example, than the one we just did. And it's far, far more complicated than problem 47 with those that look daunting, but it's a lot tamer than what it is for the capacitors and resistors and everything else. So far, I'm looking at the problems we did. This looks, according to the book, it has the highest rating in terms of difficulty. Okay, so what's the problem with this one? The key thing in here is to find the direction of this current. Again, like the key thing for the other one, the fact that the 2 points are the same voltage. The key thing in here is to find which way this current is flowing. It cannot really flow upward, because if it's going to flow upward, the indication in here is that it's going to go against this resistor. So there must be something push these batteries. Here is the reasonable assumption for it. And again, you're going to assume this value, but if it turns out to be wrong, because the sign at the end will be negative, somewhere in here where it doesn't make sense, you're going to come back and fix this issue, okay? Because these two batteries are pushing according to their directions, you don't have a choice. They didn't tell you that we made a mistake. They tell you we are sure that this is the polarity. So in this case, the current must be flowing in downward on that 7 ohm. Meaning that the difference in potential between this point, which I'm going to label it as A, and this point as being B, A is higher in potential than B. That is the bottom line. Where A is this entire point, and B is this entire point. As a matter of fact, I can find what VA minus VB is. VA minus VB, according to this reasoning, is the Ohm's law in this case, 7 times this number, 7 times 1.8. And this should be, because this one is in ohms and this one is in amps, 7 times 1.8, it's 12.6 volts, okay? I know I'm going to label stuff now. I know this point in here, which I'm going to call C, okay? There is a voltage drop of 24 volts coming this way. But from A to B, according to this calculation, is 12.6. So there must be another voltage drop in here to account for that one in here. Obviously, the current has to be in this way, in this direction. It has to be this direction. So in other words, let's do stuff in here. Let's calculate this voltage drop by requiring it the following way. So what we're saying in here is VA minus VB. It's the same thing as saying VA minus VC plus VC minus VB, correct? Since I'm coming from positive to negative, I'm really indeed dropping in here by 24 volt. And in here, since I have to compensate for it, the current must be up, so I'm going to be rising since I chose the direction for this current to be this way. If it's not, then it's going to be a disaster, because how are we going to make 12.6 equal to 24 plus another positive number? So this better be a negative number, and it's exactly 3 minus 3 times this current, which I'm going to call it I3. Again, you don't have to follow my convention. You can call it however you like to call it in here. So I'm going to call it I3. This must be 12.6 volt. This is the voltage drop between A and B. So this is 24 minus I and B. So if I move this to this side, it's going to be positive. And if I move this to the other side, it's going to be negative. And now I'm going to find the current through I3. So 3I3 is going to be 24 minus 12.6. And this is clearly is going to be positive current. That means the way I chose I3 makes sense. Okay? Because I already have 24 drop between A and C. And I cannot really have another drop. I must have a rise in here to compensate for the fact that I only have 12.6 volts drop between A and B. So that should be the difference between the two. Ri, which is 3 times I, must be the difference between 24 and 12.6. As a matter of fact, what is 12? Is it 11.4? Minus 12.6. Yeah, that's exactly how much it should be. This should be 11.4 volts. So in other words, there is a drop of 24 and a rise of 11.4. So this must be a negative 11.4, and this is 24. When I add them up, that is going to be my 12.6. Because that's how they want the current there. They want 12.6. I mean, they want 1.8. So this voltage drop between A and B, I can calculate it from here, and I'm going to find it to be 12.6. Okay? So how much the current I3? We need that current because we know part of the story. This is the same current I3 that is going through the battery. It's coming in here, and part of it, which is 1.8, is coming in here. So how much is coming from this side? That's the other question. How much is coming from here? That's the question that we need to find. And that is going to come from the conservation of charge, which is just I3 minus this number, okay? I'm sorry. This one plus that one is equal to, so the unknown plus I3 must be this I, which is 1.8 amps, okay? So we need to find this unknown current that is coming from this battery too. So let's see how the reasoning will go now. Obviously, this question mark may be positive or negative. So if it's positive, that means my direction is correct. That means this I3 better be less than 1.8. So because I'm going to move this to the other side, or at least I3 to the other side, I'm going to find that 1.8 is equal to the question mark in here. Okay, so let's find what this current is. It's easy to calculate from this equation here. Actually, I3 is equal to 11.4 divided by 3, and this is not less than 1.8. 11.4 divided by 3 is actually 3.8 amps. So what's going on now? If I take I3, which is 3.8, and move it to the other side, I'm going to find negative 2 amps. So this equation tells me that I have 1.8 minus 3.8. So it's negative 2 amps. That means this direction I chose is not correct for this current. The current is actually running down. This is actually 2 amps going down, not up. So the current that is coming in here, I have 3.8 that is coming in here, amps. 1.8 is coming in here, and 2 is coming down through this points between A and B through this way. I'm going to call this point D, by the way. So the 2 amp must be going against the battery, because this is 24 volt battery. So this battery must be less than 24. Because if it's more, then it's going to push the current against this battery and against the other one. Since it's less, I mean, since the current is running down through this direction, it must be, according to these numbers, then this EMF better be less than 24 volts. So let's check it. Let's calculate VA minus VB again through that branch. So VA minus VD, VB, we call this VB, is VA minus VD plus VD minus VB. Well, this is the EMF that we want to find. This is the drop in voltage in here, because we're coming from positive to negative. So this is the EMF that we really want to find. And this number, we found it to be 12.6 volts. We already figured it out from the beginning when we were given the current in here, okay? VD minus VB now, because we are in the same direction as the voltage, so it's just the product of the resistance, which is 2 ohms times the current, which is 2 amps. So this is actually an actual drop in polar voltage of 2 times 2. This is 2 ohms times 2 amps, and that is 4 volts. So here is the story then. The EMF must be 12.6 volts minus 4 volts, and that is 8.6 volts. Indeed, it's positive, first of all, which means that its direction is good. We don't have to flip it because they didn't tell you anything about polarity in the problem. So they are confident in its direction. So that is actually a level of confidence. The other thing also that we were worried about is the fact that, look, I have a battery pushing current in here, and I have a battery that technically should be pushing current. But during my calculation, I found the current going against it. It's coming from positive to negative in its side of it. Usually it comes from positive to negative from the outside, meaning the inside is going from negative to positive, like this battery in here. The current that we found, 3.8, is going from negative to positive, as it should. But in here, we found the current running against the battery. It's coming from positive to negative inside of it. So the only explanation that we could have for that, if its EMF, its electromotive force, is less than that of this EMF of the 24 volts. So the number that we should find for epsilon better be less. It doesn't matter, okay? If we find it more, that means we know we're wrong. Just like the example I started talking about in the beginning about the problems from mechanics when you calculate the acceleration, and the acceleration turn out to be negative because you have friction, so you have to go back and recalculate everything again because the direction of motion you chose is wrong. And if we found in here indeed that this EMF is actually more than 24 volt, either we did an error in calculation or there is something about our assumption for this current is wrong, okay? So this is basically the whole picture told now. So it's a positive, so it's a good deal. Now you can go back and check the voltage drop. Remember, the voltage drop is 12.6 and it's 8.6 here plus 4 because 2 times 2 is 4. So that's 12.6. On this side, it's 7 times 1.8, and that is actually 12.6. That's exactly how we found it. On this side, it's still 12.6 because there is a drop of 24, but a rise of an 11.4 when we're coming this way because we're going against current, okay? The current that is being pushed by this very same battery, okay? So in this case, since we're coming down against the battery, we're going against the current. So this is a drop, and this is a rise, and that is also 12.6. Everything makes sense. Okay, the current story, we have 3.8 coming in here, 1.8, as they want us to go through this 7 ohm, they want 1.8, we gave you 1.8. So 2 must be going in the opposite direction. Okay, so we still have about a minute. Here is the deal. On Thursday when we meet, we're going to start a brand new topic, chapter 27, because we have still quite few of topics to cover. And next week is spring break, and the week after is exams or midterms. So we're losing 2 weeks in the process. I know one of them is normal week to lose anyway, spring break, that's accounted for. But the one that is not accounted for is the week after. So we're going to start chapter 27. We're going to do the exam after that, and then we're going to do the problems for chapter 27 immediately the week after that, and then we're going to continue our story with the with this class. And I don't think that the lab is ready for this weekend. We did lab 4, so that is the lab that we have. The next lab is about the AC circuit and magnetism. I'm going to flip the magnetism and circuit immediately when we come back after the spring break, and most likely we're going to start the lab right during the exam week. Okay, so you'll have that lab during that time, and then in addition to the lab for the magnetism. Make sense? So there is no class this Thursday unless you guys want to meet and talk about problems. That's going to be an option 2. Make sense?
Yes.
Yes.
It's clear.
But wait, do we still have the morning class on Thursday?
Thursday, absolutely. That's when we have to do magnetism. We have to really catch up on these things. We have class on Thursday morning.
Okay, make sure, because you just said no class a few seconds ago, and I was making sure.
The afternoon, the lab.
Oh, okay. Thank you, Professor.
No problem. Okay. So I'm going to stop this recording here.